Hi everybody, and welcome to Chapter 12. This is the chapter which discusses functions and will most likely be the final chapter that we'll consider in the course. We might have a little time to sneak in another topic at the end, but functions are so central to mathematics that it's worth making sure that we get as much out of this chapter as we can. You have all been using functions for many, many years. In fact, I think functions are part of the middle school mathematics curriculum. And I think what's embedded in everybody's minds is that a function is a kind of a rule where you plug in a number or something and you get out of something. And so that function could be f of x equals x squared. You plug in 3 and you get out 9. Or the function could be sine of x, and you plug in pi over 2 and you get 1. And you've probably also heard some of the terminology around functions like domain and range. And what we're going to do in the next chapter is we're first of all going to do to functions what we did to relations, which is we are going to abstract the notion of a function. And in particular, we're going to deal with this word rule, which is very hard to define, and get rid of it. And we're going to replace the definition of a function with something very simple, but rather abstract using set theory. And then we're going to use that abstract definition of a function to study different properties of functions and eventually prove some theorems about functions, which you have probably seen before in different forms. So let's see how things go. So, as I mentioned in my little introduction there, the way you have probably been thinking about a function up to this point in your mathematical studies is that you're given some kind of a formula, like f of x equals sine of x, and you think of it as a rule where you plug in x and out comes the value sine of x. And one of the most useful ways to visualize something like this is to draw the graph of the function. And let's think about what this graph is. So first of all, this function f has an input set of numbers, which is its domain, the real numbers, and an output set of functions, also real numbers. And I'm going to be a little cautious about what we call this set. You may have heard it called range, but strictly speaking, it's called the codomain. And I'll explain later the difference between the range and the codomain. So a function has a domain, which is where the input values come from, and a codomain, which is where the output values land. And to draw the graph of the function, we construct the Cartesian product of the domain and the codomain. So here we have R cross R. And thanks to what we've learned so far in this class, we know that R cross R, the Cartesian product of the real numbers with itself, is the collection of pairs x, y, ordered pairs, where both x and y are real numbers. And then what we do is we pick out of this big set, this big Cartesian product, the points where the x coordinate is given by x, and the y-coordinate is given by f of x, or in other words, in this case, x sine of x. So the red points in this picture, the graph of f, which are the red points, is precisely the set of pairs x, y, where y is sine of x. Now, obviously, I haven't drawn the whole thing. I mean, I sort of ran out of steam here, but in principle, this goes on, as does the x and y axes, to cover all of the real numbers. And so what we see from this picture is that the graph of a function is a subset of the Cartesian product of the domain with the codomain. And it's the subset given by points of the form x f of x. Well, this idea of a function as a subset of a Cartesian product of two sets should take you back to the last chapter, where we defined relations to be pretty much arbitrary subsets, a relation between two on a set A, to be pretty much any subset of the Cartesian product A cross A. And we also talked about relations between two sets as pretty much any subset of the Cartesian product of A cross B. And this is the key insight for us to take the notion of function and get an abstract definition of it, which doesn't rely on this word rule that we can't really describe. So, as I mentioned before, if you have a function f which has domain A and codomain B, and here remember, codomain, this B is just a set big enough to hold all the values of f, then the graph of f is the set of points consisting of pairs AB, where A is chosen from A and B is chosen from B, and the point B is given by f of A, where f is some formula or rule or something. And the things that we want to observe about this is that this G, the graph of f, is a relation from the set A to the set B. It's a subset of the Cartesian product of A cross B, and that's the definition of a relation. But the other thing to realize about this set G is it tells us anything we might want to know. If we know the set of the subset G, we know everything we need to know about f, because if we know all the points of the form A f of A, and we want to know, for instance, what's f of 3, we look for the ordered pair whose first coordinate is 3. So in other words, so suppose we're given G, what is f of 3 in our old notation? Well, we look for the ordered pair whose first entry is 3 and whose second entry is something. And then we know that y is f of 3. In the terms of the picture, what that's saying is if all we knew was the graph, all we knew was the picture, and we wanted to know the value of the function at 0, we would take the point 0 and we would go up and find the point on the graph above 0, and that would be the value of the function at that point. And just to reiterate this, the two sets that are involved here are called the domain and the codomain of the function, and the graph is a subset of the Cartesian product of the domain and the codomain. So far this is kind of descriptive. And now what we're going to do is we're going to turn it on its head and we're going to make it into a definition. So what is special about a relation which comes from a function? Well, here's a chance to practice your quantifiers. The key property that makes a relation into a function is the following fact. For every point in the domain A, there is a unique B in B so that the pair AB belongs to G. So I should say here, a general relation G of F, let's just call it G. A general relation G is a function if it has the property that for every A in the domain, there's a unique B in the codomain so that the pair AB belongs to this set. This is quite different for a general relation. Remember, a general relation could be any subset of A cross B. And we did look at some other properties of relations like the reflexive property or the symmetric property, and those were quite different. I mean, for example, the reflexive property said that every pair of the form A comma A is in the relation. And this is different. This condition right here is has a for all there exists structure. And the way to read it, remember, is that if you pick any A in the set A, you can find exactly one B in the set B so that the pair AB belongs to G. So here's a picture of the situation. Here are domain and codomain are both the integers 0, 1, 2, up to 9. On the left-hand side, I've drawn an arbitrary subset of that Cartesian product. The red dots are an arbitrary subset of the Cartesian product of A with B. On the left-hand side, I've drawn a function on the same domain and codomain. So remember, the condition from the previous slide that makes the green dots a function are for every A in A, there exists a unique B in B so that AB is in the set G. So let's test it. If A is 0, there is only one B so that AB is in the set. So that means that the set that 0, 6 is in the set of green points. 1, 9 is in the set of green points. 2, 8 is in the set of green points. 3, 3 is in the set of green points. 4, 4 is in the set of green points. 5, 0 is in the set of green points. 6, 6 is in the set of green points. 7, 3 is in the set of green points. 8, 3 is in the set of green points. And 9, 2 is in the set of green points. So notice that for each point in the domain, there is only one point in the combined set which has that point in its first coordinate. And you may have learned this before as the vertical line test. If you draw the Cartesian product of A cross B as an xy plane in the usual way, then the test to see whether the points form a function is the condition that every vertical line only hits exactly one point. Now it has to hit a point because the condition is for every point in the domain there exists a point in the codomain, but that point has to be unique. So if we look at the relation just by way of comparison, it's still true that for every point in the x-axis, for every point in the domain, there exists a point in the codomain. So that part's okay. But the problem is that there are multiple such points. And so this is not a function. And if you think about the idea that we're trying to capture a rule, here we have a rule. We say if you want to know what the value of our function is at 3, for example, you go to 3 and you go up until you hit the first and only point that lies above 3, and the y-coordinate there is the value of your function. Whereas here it's ambiguous. I mean, you don't know what value to give to 7 because there's too many choices. So a function is a relation which has this very special property that for every point in its domain, there exists a unique point in its codomain. Maybe I should put it this way. For every A in the domain, there exists a unique B in the codomain so that AB belongs to the set. Now, we can draw functions in other ways as well, just like we can draw relations in other ways as well, by using, for instance, arrows connecting their domain to their codomain. So here, let's look down here at this little picture first. Here we have a function. The arrows go from the domain to the codomain, and you see that each arrow that starts on the left only hits one point on the right. So for every, I'm just going to write this again, for every A in the domain, there exists a unique B in the codomain such that AB is in the function f. So this is a picture of the function f. And we can write them down. The pairs are AA, BA, EB, DB, and CB. Now, notice that some points in the codomain get used more than once. That's okay. The condition says just that this, if you just look at if you fix the first coordinate, there has to be a unique value for the second coordinate. It doesn't say that for every value of the second coordinate, there's a unique element in the first coordinate. So this is a chance to think about how the order of the quantifiers matter. And there's also some points in the codomain which aren't hit. But there's no problem with that either because nothing in the definition says that. The definition starts with for every A in the domain, there has to exist a B in the codomain for which AB is in the function. So the fact that there's no A in the domain for which C is the second coordinate is not a problem given the way these quantifiers are written. This picture is not a function, because you see that A is connected to both D and C. So this is a relation. A and D are related, and A and C are related, but it's not a function because there isn't a unique element of the codomain associated with each element, with the element A of the domain. So remember, to prove something is not a function, you have to prove that there exists, so not a function, will negate the quantifiers. There exists an A in the domain such that for all B in the codomain, either A, B is not in G. I mean, we have to contradict there exists a unique. So to say that there does not exist a unique thing either says there's nothing or there's more than one. So to be a function is to say that for every A in the domain, there exists a unique B in the codomain such that AB belongs to the function. To not be a function means that there exists an A in the domain such that for all B in the codomain, well, so that either one of two things is true. There is no B in the codomain such that AB is in G, or there exist two different ones that are in the codomain. And that's because when you negate there exists a unique, the two possibilities are there doesn't exist or there exists more than one. So in this picture, we have all sorts of things happening. In the case of A, there's more than one point happening. There's more than one point in the graph where the second coordinates are different. So that's not a function. The last couple pieces of terminology about functions to get on the record are the idea of a range of a function. So this is a term you may have heard before, and it may clash with your understanding of this weird word codomain. So remember that a function f is defined. So let me give you, let's give the definition of a function first. A function f is a subset of the Cartesian product of A cross B where for all A and A, there is a unique B and B such that A, B is in F. And in this situation, A is called the domain. B is called the codomain. But as we've seen, the codomain may be much larger than it needs to be. Just to flip back a little bit, if you remember this example of sine of x, the codomain here was the real numbers. But the function only takes values between -1 and 1. So even though we have this great big codomain, we don't ever use a lot of the values that occur in the codomain. And if you go back to look at this picture here, this was a function, remember, but we have these points C, D, and E in the codomain, and the function, there's no ordered pair for which C, D, or E ever occur as the second factor. So to capture this distinction between the codomain, which is the big set where you're sure that all of the values of the function land, and the actual values that the function takes on, you use the idea of the range. So the range, it's given right here, the range of a function is the set of B and B for which there exists an A and A so that A, B is in F. So in old-fashioned terms, the range of F is the set of B for which there exists an A such that F of A equals B. As you can see, you can't survive this without getting the quantifiers right. So to go back to these pictures, this A has a point in the domain for which F of A hits that. So the range consists of this point and this point. And these points are not in the range. So in the picture, oops. I guess I can't copy this. I'm not sure why not. Oh, because I know why not. Never mind. So, but if you remember that picture, in this picture, the points that don't occur in any ordered pairs don't make up the range. And in the sine of x picture, the range is just the range of sine of x is the collection of points -1, 1. Because any point in the interval from -1 to 1 can be obtained as a value of sine of x. So you may have seen this business of the range as coming from the horizontal line test. If a horizontal line hits the graph, then that point is in the range. It's hard to use the horizontal line test when you have your function expressed in this form. Here, you would want to know the points in the range are the ones which have arrows which end at them. So here's one example of a range, a computation of a range taken from the book. It's example 12.3. So we look at a function phi, which takes a pair of integers m and n, and gives us the value 6m minus 9n. So in our fancy new notation, or a new way of thinking about functions, phi is actually a subset of z2 cross z, consisting of all pairs mn, that's a pair, and then the value 6m minus 9n. And the range is which values are possible. As m and n runs over z2, which values of 6m minus 9n are possible? Well, one thing to observe is that 6m minus 9n is 3 times 2m minus 3n. So if we were to plug in values of m and n, I can even make a little picture here. Let's do minus 2, minus 1, minus 0, 1, 2, 1, 2, minus 1, minus 2. If we let this be the m-axis and this be the n-axis, then when m is 1 and n is 0, this is 6, and then this is 12, and this is minus 6, and this is minus 12. And then the next row down, we've done this before, you get a grid of arithmetic progressions. A step this way means you subtract 9, so you get minus 3, and then 3, and so on. And then you take another step down this way and subtract 9 again, and you get minus 12, and then you get minus 9, and so on. And minus 6, and so on. And so you notice that one thing you should notice is that all of the numbers in this grid are multiples of 3, and that should be pretty clear because what we're computing is multiples of 3. So the range of f includes only multiples of 3. Or in set theoretic terms, the set of x such that 3 divides x is contained in the range of phi. But a reasonable question would be, are they equal? Can you get every multiple of 3 out of this function? And here we can use a theorem that we proved earlier in the book. We can use Euclid's algorithm, which tells us that the set of values of 6m minus 9n is precisely equal to the multiples of the greatest common divisor of 6 and 9, which is exactly the multiples of 3. So in fact, we know that every multiple of 3 is of the form 6m minus 9n, using Euclid's algorithm that we proved before. So by Euclid's algorithm, the range of phi, I drew this goes the wrong way. Every element of the range of phi is divisible by 3, and then by Euclid's algorithm, the range of phi every element that's divisible by 3 is in the range of phi. So the range of phi is actually equal to the set of multiples of 3. I think I will stop here and put this into a separate video because this video has gotten long enough.